This is the okay. So it's recording. So yeah, I'm going to talk about ZXLive, and so this is the repo for ZXLive where the code is. It's open source, and it's currently actively being developed. And so this is like a very early preview of what ZXLive is, and part of the motivation for this talk is that it is to so there are two reasons. One is to like show everyone what we have been working on and like all the cool stuff we can do with it, but also more importantly to get feedback from you all and like ask what features you would like added to ZXLive and what we should add more, and also like an invitation to just contribute and use ZXLive and just try it out and let us know what we should add. And if you're interested in contributing, also reach out for that. So ZXLive is this project, and it has been contributed so far by 18 people. So like here's the list of all the contributors, and you can see that it's been actively contributed by a lot of people. So anyway, I'll start the demo. So here's what it looks like. So first of all, the screen, for people who are familiar with Tikzit, this interface probably looks familiar. And it's because we try to make it similar to that, at least. So this is the edit mode, and here we can like create circuits, we can create graphs, we can create diagrams, and so on. So let me start with an example. So I'll start creating a circuit. So these are the boundary nodes. And let's do a very simple example. So I will do the simple example that's used quite often in giving ZX demos. So which is that if you have 3 C nodes, it becomes a slop. Oh, not left. I need to add the edges. So all the shortcuts that you might be familiar with from Tikzit, most of them should work here. So this should be quite familiar experience for most people. But anyway, so now we have the example circuit that we want to simplify. And so once we have the circuit, once we have created the drawing, once we have created the diagram, we can start the derivation by clicking this start derivation button here. And you can see that there are, so this is the interface for the proof mode. And you can see that there is a bunch of rules on this side that you can see on the left-hand side. So most of these rules are implemented in physics. So here are our basic rules. These are some more rules that are applicable to graph-like ZX diagrams. And we also have rules for the ZXW calculus and ZH calculus. But obviously more needs to be added for other calculi. These are only few rules. And this in the last section is the simplification rewrite routines that are implemented in physics as well. One thing that I skipped are the custom rules, but yeah, we'll come back to this. This is like rules that you can create and add to ZXLive. So anyway, let's try to prove the let's try to prove the famous 3 C naught equals swap identity. So what I can do here is I want to apply bialgebra. So what I will do is I'll take this Z and I'll drop it on X, and this will apply the bialgebra. So on the right hand side, you can see the proof history. So if I go back, like you can see that this was the initial diagram. We applied bialgebra, and we get this. Now I can drag this spider on X to fuse. I can drag this here to fuse again. And since there were 2 edges, they cancel out because of the Hopf law. I can do the fusion again here. So this is fused, and so now I can. So now I have this identity spider that I. Sorry, was that a question? Anyway, so there is an identity spider here that I want to remove. So either I can like click the remove identity rule here, or there's also an identity spider here. What I can use is this magic wand tool that you see on the top left corner here. So I'll use this magic wand tool, and I can simply just slice it like Fruit Ninja. So after doing that, we fuse again here, and now 2 more slicing by the magic wand tool, and we have the identity. So now this is a swap. So we have started from here, and we proved through each rewrite step that 3 C0 is indeed a swap. Now, what I can do is I can, first of all, save this proof. So I can just say 3 C0 equals swap proof. And then I can later reload this. So is that a question? Okay. So I can save this proof and I can reload it later. But another thing that I can do, which is quite fun, is that I can export this proof to Tix. So I can write this proof. So I can save this proof as a Tix diagram. And if I go here, I can open the Tix diagram in Tikzit, and you can see that it has typesetted the whole diagram for me, so I can actually preview it, and you can see that it has typesetted the proof. For some reason, the equalities are not aligned properly, but yeah, I'm not sure why. But in theory, once we fix this, you should be able to just do your proof in ZXLive and import it to your papers in LaTeX. So I mean, since it's Tikzit, I can just simply fix this by dragging them to the right position. Anyway, that's better. And you can see that it automatically gives me the name of equalities that I've used on top of the equal sign. So you don't need to go and manually add these equalities. And in fact, this is all configurable. So actually, if I go back to ZXLive, if I go to preferences, you can see that I can give the LaTeX command for each of the rule, and you can modify all the rules. And in fact, you can also give LaTeX command which links to your lemma in your, for example, rule table, and so it should just work automatically. So you don't need to remember each step. So that's quite handy. But anyway, so we proved this. We proved this proof. We proved this equality. Now, what I want to do is that I want to be able to use this equality in other circuits that I want to use in future. So what I can do is I can go to rewrite, and I can save this proof as a lemma. And what it will do, so I need to give it a name. So we call it 3C0 equals swap. And what this will do is it will allow me to use this result in future proofs. So I'm going to save this as a lemma. And now let me open a circuit where we can like use this. So I have this circuit here, which is a Clifford circuit. And you can see that there will be some C0s that we might be able to cancel. But it's very big. Okay, let's start doing this example and see how we can simplify this. So this. Right, so let's start with so what we can do is here we have a pi. We can push the pi through the green. So I can apply the push Pauli rule. Now it's here. I can fuse this. I can push the green pi through the red node here, again using the push Pauli rule, and fuse. And we see that, okay, now we have something that looks almost like a 3C not equal swap, but this X is connected to more legs. So we will use the magic wand tool to simply slice off the leg. So now we have 3 alternating C nodes. Well, there is also, oh, sorry. So now what I can do is I can simply select these, but there's also phases here. So let me also unfuse them. So now I get the exact match. No, I'm using the magic wand tool to, okay, so.
The smaller area is the part that you want to
yeah, so I want to like decide which, maybe can you just, so I want to decide when I fuse where the phase should go. So what you can do is that you can hold shift while dragging the magic wand tool, and this tells us it gives us the ability to choose which phase should go where. So like I want 0 phase on the left spider. So wait, that didn't work. Well, okay. Anyway, that worked. So now I have the 3 alternating C nodes that we had in the lemma, and you can see that here in the custom rules there is already the rule added. So now when I select the 3 alternating C nodes, you can see that the custom rule 3C not equals swap that we proved is activated. So I can just click that, and now those 3 C nodes have become a swap. I can do further simplifications, so more fusion, or if I don't want to like individually do fusion, I can also just select a bunch of things and just click on fuse spider, click on fuse spiders. Or I can go to simplification routines, and here it gives me all the simplification routines from physics. So let me do all the spider fusion. Oh, right, there is no more spider fusion left. Okay, that makes sense. So what can I do more? Okay, I can pass this through. Now I can do more fusion. Now the good thing about ZXLive is that you can already use simplification routines from physics. And I know that this is a Clifford circuit. So what I can do is I can just select everything, and then I say, apply the Clifford simplification routine from physics. And this gives me the simplified diagram. I can also double click these nodes to change color. So now I have this diagram, which looks like what it would be in the Clifford form. Okay, so yeah, let me also try to see if the export to Tikzit works in this case. Okay, nope, that doesn't compile. Okay. Oh, let's not worry about that. Anyway, now I want to give another example. So another way to create custom rewrites is you can just go to rewrite and click on new rewrite. And this gives you like a side-by-side view. So what I can do here is I can just simply write down the left-hand side and the right-hand side of the rewrite rule. So suppose we have two C naughts, and I want to show that okay, when you have two C naughts, they can cancel out. So we can create the rewrite here. So I'm drawing the left-hand side, and the right-hand side is simply two identity wires. So let me call it two C naughts. Cancel. Okay, so it gives me the warning that the left-hand side and the right-hand side of the rule differ by a scalar, but I think that's okay for now. And cancel. Let me open another graph, which will be, which I've created for this. So last time when we were trying to apply the custom rewrite, we had to do the unfusion quite a lot. So like this is a very common occurrence where you want to like unfuse and like apply the rewrite rule, and that was a bit inconvenient. But turns out in ZXLive, the custom rewrites actually understand that that when you have Z spiders, you may want to just cancel. Sorry, Z and X, or when you have spiders, you may want to automatically you may also automatically want to unfuse things. So what it allows you to do is you select, it should show up here, but it doesn't. What's going on? Leah, do you know why this is not showing up?
Why what's not showing up?
Why the 2C naught does not show up here?
Because this is the two C naughts without the pi over two phase.
Oh, right.
Like you
yes,
said
of
you wanted
course. Yes. Okay, so pi over two phase was the problem. Okay, anyway, but now if you select yes, 2C naughts equal swap shows up, and you can see that the there are more wires connected to the X and Z here. So to exactly match this, you would need to like unfuse them. But now when you select it, you can apply this.
Yes. Okay, you can carry on. Sorry.
So yeah, I just mentioned that it can perform the unfusion automatically and apply the rewrite rule. Anyway, now I want to move to a more interesting example of rewrites with symbolic variables. Let me close all of this stuff. Let me open the graph that I've created before. So this is an example of two phase gadgets, and what we can do here. So I should highlight this. These are just arbitrary variables like A and B, and these are like symbolic. These are symbolic values, and they are not direct specific pi by 2 or pi by 4, anything like that. And ZXLive already also supports variables, and you can see that there are variables A and B listed here. You can change the types of them as well. So they can be arbitrary parameters, or they can also be Boolean. So these the Booleans would be useful, for example, when you're describing measurements, where you can write A pi, B pi. So that's relevant in MPQC, error correction, that sort of things. But let's say we have these two phase gadgets with parameters A and B. And what I want to do now is I want to prove phase gadget fusion. So what should happen is that when you have these two phase gadgets and you fuse them, they should become a single phase gadget with the phase A plus B. So I will do that by first fusing the legs here. And then now you can see that I can apply by algebra if I look at it this way. So I'll apply the algebra rule in the reverse direction. So it gives me this. And now I can fuse these and the fusion gives me A plus B. So what we have shown is that if you have two phase gadgets, they fuse to a single phase gadget with the phase A plus B. Now I'm going to save this as a lemma, and I'm going to call it phase gadget fusion Okay, so now we have saved this lemma. What's interesting is that I can actually apply this to specific instances. So this lemma that we proved were for arbitrary variables. But now if I had specific instances of this, so let's say here, instead of A, I had like pi by 2. And instead of B, I had pi by 3. And if and now I can see that there is the phase gadget fusion here. I can select this, and you can see that it's already highlighted, so I can apply the phase gadget fusion rule. And what it has done is it has fused the two phase gadgets, and because we were working with symbolic variables, it knew that it had to add the phases. So it simply performed the addition of pi by 2 and pi by 3 and gave us 5 pi by 6. So you can create custom rules with these variables, and you can apply them to specific instances in your rewrite. Now, so now I want to create a slightly more complicated example. And here I want to show phase gadget anti-commutation. So this new rule is where if you have two phase gadgets that have different legs, so instead of having two Z and Z, it might have Z and X leg. When they commute, you get a Hadamard edge between the X. So let me first draw what I'm describing. So let's say we have a phase gadget with an X, which means it just conjugated by the Hadamard. And now what I want to do is that I want to show that this rule works in general. So what I'm going to do is I'm going to simply do it for one leg and then leave the wires open. And what this means is that regardless of what phase you have, or if the X has multiple legs, this should still work because because ZXLive recognizes the fact that you can always unfuse and apply the rewrite rule. So I'm going to leave these the legs open, and I want to show that, okay, when you have this, and when you anti-commute this, so in that case, what will happen is that these two will change sides. So let me move them around. But they should still be connected to the same inputs. So like this. So when they commute with each other, you get a Hadamard edge between the X's. So I can create a Hadamard edge between them like this. And now I will save this and like try to apply it to the phase gadget with multiple legs. So let's call it phase gadget anti-commutation. For vascular, doesn't matter. Okay, so we have saved this rule, and now I'm going to create a new graph where, let's say, we have more wires. Let's say we have 2 wires, and it's a phase gadget on 2. So this might be connected like this. And this might be specific scalars that we have, sorry, specific phases. So let's say this is pi by 2. This is pi by 3. And this phase again just should be connected with more legs. Okay, so now I want to show that you can actually commute these phase gadgets, and when you commute this phase gadget with this phase gadget, they will commute and you will get a Hadamard edge between the x's. So let's try to do that. So as a first step, I'm going to select the rule that we applied. So this is the part where I want to apply the anti-commutation rule. So I select that, I click here on my custom rules. It gives me phase gadget anti-commutation. I'm going to position them better. And you can see that it has given me this Hadamard edge here. So it was like this. I applied the phase gadget commutation. Now they have been commuted. And since there were more legs going out of the x's, it automatically unfused, so we can fuse it back. So now you can see that the top part, which was the x leg of the phase gadget and the z leg, which anti-commute, we have now commuted them past each other, and as a result, we have obtained the Hadamard edge. Now I can also just make it look better. I can move this too, and to the bottom legs are just 2z, so they should commute through each other. So I fuse them first, and then I use the magic wand to simply cut the legs so that they are in 2 different sides. So we have this original phase gadget, and now it has commuted past. They have commuted past each other, and they have obtained the Hadamard edge as a consequence. And here the rule it used was this one, where it was allowed to take arbitrary number of legs as input here, because it can automatically unfuse. So yeah, this is like some of the things you can do with ZXLive. I think next I want to just open the room for discussion so that we can talk about what more features we should have, or just questions about the things that I've shown today.
All right, thank you very much, Razin. Yeah, if there's any questions from the room.
Yeah, hi. Let me show my face. Hi, a really cool talk and really useful tool. So just in terms of setup, when I were to download this from GitHub, then the basic rules and all the graph-like rules and stuff, they're already there, except for the custom rules. I'd have to make those myself.
Yes, that's right.
Correct? Okay, okay. Yeah, and then I think instructions from just following the instructions from the GitHub page should be sufficient. Cool.
Yeah, I think it should work. You just need Python installed, and like
Yes.
you clone the repo and do these 3 commands.
Nice.
So Razin, if you don't mind, if I can also add some.
Yeah, go ahead.
Yeah. So also these custom rules, they are saved in a folder, and you can say in your preferences where they are stored. So like if you're working with someone else, you can sort of like you could send these files to the other person, and they add them to the custom rules folder, and then you can share these custom rules.
So this is the lemmas folder that I have here, and like all my custom rules are stored here. And you can just pick where your rules are stored, so you can give the path.
Nice. Nice. I wish it was ready before I finished writing my thesis, but no. I can do that later. Awesome. Thanks.
Oh, by the way, we also have more color schemes. So if anyone is a fan of classic green and red, or you like the white and gray from the Dojo book, yeah.
Yes, does it import from text as well?
Yes. So maybe I can.
Figured.
So here, yes. So you can import from any of these formats. So so this is the physics format. You can import from Chasm. You can import from Tigs, JSON, and you can also import the ZX proofs and ZX rules. So all of these are supported. So for if you're importing from Tikzit, but like from Tigs, you may want to like so for Tigs import, you have the settings. So in your Tigs style file, you would have like style for each node, and you can specify what Tigs style should be referred to as. So it should be interpreted as the Z spider, and what should be interpreted as the X spider. So if you have a specific style in your Tigs style, you can tell the ZXLive how to interpret that style in the generators that it supports.
Cool.
I should also add that one of my favorite features, I think, is you can so I think don't think I've seen shared, but you can copy paste things inside Tikzit, but you can also, if you Control Shift C and Control Shift V, you paste to the clipboard, and then you can, it's like saved as tick, so you can instantly import it into Tikzit. So you could like do something in Tikzit, copy it, and then paste it in ZXLive, and it will just work.
Nice.
So I've copied this, and like I'm going to create a new Tikzit, so I can just paste this diagram that I copied here in Tikzit. So yeah, it should work quite well with Tikzit.
Nice.
I forgot to mention that we also support the H box from ZH, and the W and node from ZW, and the Z box from ZXW or algebraic ZX. Maybe I should give an example of what the W looks like, because it's kind of different, because everything else is a spider, whereas W could be like it has a direction. So what you can do is you can the W has two parts. One is the top part, which is like the input sort of, and the W in ZXW only takes one input. So you can so this specifies what the input is. And let's say, let me do one more here. Like this. I have one more so we can connect the output to the input. And the top node, you can also use it to like rotate the W. So you can have something like this. And you let me put a high on top here. This is like an example of a Hamiltonian, for instance, where W represents the summation of the Pauli strings xz plus zz plus zz, and this W, for example, also does the fusion and this sort of things. So anyway. Yeah, it's kind of nice that we can also implement non-flexsymmetric nodes in ZXLive.
Will it enforce that you only have a single input on your W node?
Yes. So for W, since we only want one input, like if I try to make any other edges, it wouldn't work. You can see it just yeah, it doesn't let you.
I think also if you make an ill-formed diagram and you try to start a derivation, it will just say that it's ill-formed. So if you have like a boundary node that's not connected to any spider, for instance.
Like for example, if your boundary node connected to two spiders connected to the same boundary node, that does not make sense. So it will just say graph is not well formed. And yeah. Or if you have just a random boundary node, that should also tell you that it's not well formed.
So thank you for the very nice talk. I had a few questions about some of the functionality that you demonstrated. Earlier, you were trying to use a rule, and you had a pi/2 phase on one of the nodes, and it seemed intuitive to you, and I guess probably many of the viewers, that you should be able to do this because you know that you can split off the node and take out all the phase that you need. While I guess it's probably not intuitive for the computer, because what phase do you take out to be able to make every, you have to check for every single rule in the list as to whether or not you could apply it. But do you think there's a way to potentially make that work? John is nodding.
Yeah, I think so. I just but there is a slight problem, because if my rule so actually let me open the rewrite rule and maybe like argue why it's maybe not so
there's a very good argument for why it's not obvious, right? Like if your rule has any sort of parameterized phase, for example.
Yeah. So if I had let's say my rule was something like this, where this needs to be pi/3 to cancel, for instance, and I saw this here, I would not know that it needs to cancel. It needs to know that it needs to cancel a specific amount for it to match. But I think that's possible. I think what it needs is that so right now it does not support phases, but I think what it could do is that it can unfuse the amount it needs. So here it needs let's say pi/3. So whatever we have here, it can do maybe something like so let me try if it works with this. So I hold shift. So let's say I want pi/3 on one of the, for some reason this is not working. So it could perhaps like just say, okay, this has to be pi/3, and it then adds whatever phase it needs to add here from pi/2 to make the rule match. So I think that's probably possible to add.
Additionally, earlier you were removing phase-free nodes with exactly 2 incident edges by cutting through them with the magic wand. I can probably guess as to how the implementation of the magic, because I can figure out how the implementation of the magic wand looks at where you start drawing and where you end drawing to figure out where to slice. It's very clever. However, it did feel a little clunky to like have to go click the magic wand and then like slice through the node. Maybe a double click perhaps would be sufficient to destroy phase-free nodes with 2 incident edges, since it seems like a common enough and desirable enough operation. Oh, I see. Double click is changing color. I understand.
So, yeah. So we chose double click is changing color, but maybe that's more intuitive to use double click to destroy phase-free nodes.
Well, I think maybe we want to give very common operations a keyboard shortcut. Like remove identity will just be like R or like I for identity or something. And then
that's a good idea.
I mean, for in any case, like now I think Razin, for demonstration purposes, he like manually selected the magic wand tool and then the selection tool, but like S and W switch between the tools, so you can also use the keyboard shortcuts to quickly switch to a tool and then remove it.
Yeah, that's just S and W.
I don't want to hog the floor. I have a couple more quick questions. So it seems like a very, very nice tool for using to make diagrams for various papers. is there a snap to grid option? It wasn't demonstrated, but maybe it's there. Yeah, okay, great. John is nodding. And additionally, I have not used Tikzit much in my life. I've tended to make manual Tix diagrams. Is there a way to get the individual diagrams from the derivation instead of the long derivation, which might be like messier than what I actually want to show my, okay, great. So
Yeah,
and my
I
final
can
question. Oh, sorry.
I can
Yeah.
just copy this, paste it in a new thing, and then I can save this as Tix, export to Tix, and that would be just one step.
I see. So every
Maybe it's
step,
useful to
like
have
I take the derivation, I go to the step that I want, I copy that diagram. Sure. Okay.
maybe it would be useful to just have a feature where you right click the step and it gives you the option to copy the or like save export specific step to Tix.
Or maybe you could export the entire derivation as a large number of Tix files, and then
Oh, I see. Yeah, I mean, okay, that sounds useful. Yeah, it could be like a series of Tix file rather than like a one big Tix file.
and my final
think-
question.
I think there was also a feature that Contomatic also had, where like you instead create a folder, and in this folder is like a series of files that are like all the steps of proof. So yeah, I think that should not be too hard to do.
When you make a derivation, sorry, not a derivation, a rewrite rule. Yes, like that. Is there a check that tells you that checks whether or not it's valid or if it's nonsense?
Yeah.
Okay, I see.
So let's
Because
say
like Quantumatic as the natural comparison software, of course, it would not let you screw it up, in that it forced you to follow rules. And here it seemed like you were freehanding the whole thing.
So
But
I mean,
okay,
you can see that when I try to save this, it actually gives me a warning that they differ by a scalar. But if I had like something which was completely maybe not this, maybe this was completely incorrect,
Uh-huh.
and I tried to save this, it would just say they have different semantics.
Very cool.
What it does not do is that like it gives you the warning, but if you still want to go ahead, you can. So because I think the motivation was that maybe, yeah, I don't know, maybe in future we want to support custom generators where you can create a custom generator like a black box where you can say, okay, this has 3 inputs, 2 outputs, and for which we may not have like semantics. So we may want to support these custom rewrites for custom generators, and for which we may not have like the linear map.
I see. And so you're saying it does not currently support bang boxes?
No, I think we have had many conversations about bang boxes, and there has been almost an agreement that the thing that makes Quantumatic the main drawback and the main reason for failure for Quantumatic was bang boxes. So we don't want to support bang boxes at this stage. However, we have discussed alternatives, like, so we think we can support scalable ZX quite easily once we implement custom generators. So that would be like an alternative to bang boxes. And the reason why that's probably not going to make everything very slow and like take a lot of time to match is because you can always just convert from a diagram to its like scalable ZX form, and then the rewrites in the scalable ZX don't have to check for like arbitrary number of wires. It's just like a custom rule with a special generator where so we are discussing that maybe it's more reasonable to have something like scalable ZX instead of bang boxes where you can like keep multiplying, or like keep increasing the nodes, and like it takes forever to find matches.
Thank you for answering all my questions. And thank you.
If I can add a little bit to that about because the obvious comparison of this software is with Quantomatic, because that's also a graphical proof assistant for these kinds of diagrams. So like I think our main motivation was that Quantomatic is a very general tool. You can construct, you can have any type of generators, and you can create any type of rewrite rule. And this generality also makes it a bit clunky to use, where like you have to sort of do more steps for certain simple things. And here, because we know the targeted ZX diagrams, we can make some very nice shortcuts, like just dragging two spiders on top of each other, fuses them, or does a bialgebra, which, yeah, or just like slicing, splits a spider or moves an identity. And this just makes it like easier and more fun to use. And yeah, like my reasoning for not wanting bank boxes in ZXLive is that if your rewrite rule becomes complicated enough to use bank boxes, then probably maybe you want to have like an extension to physics, where like you create a custom script, a custom Python script that just like implements a rewrite rule, like local implementation and pivoting, for instance, which are also families of rewrite rules. They are just like a built-in functionality from physics, which is how they work, even though they target like any number of wires. Which, I mean, even in Quantomatic, you couldn't represent these because they are not representable by bank boxes. So yeah, anyway, that's my 2 cents about this. Robert, I see you're unmuted. Did you have a question?
Yeah, unfortunately, my internet dropped out for a second, so I don't know if someone asked this question already, but how easy is it to extend with custom generators? Most ZX papers at the moment implement new syntax for their arguments. How easy is it to use such a tool, this tool for these kinds of extensions?
I think adding custom generators should be fairly easy, but I mean, conceptually it's not that complicated, but like we haven't implemented that. But I think the way it would work is that you will need to support like a custom type for in the physics data structure. So ZXLive internally uses physics, and for this custom types, you can add extra data that you want. So you can specify how many inputs it has, how many outputs it has, and things like that. So, I mean, once the custom generator feature has been implemented, it should be quite easy to use, I think.
I see. And sort of related question on the practicality of using this for the articles I write. A lot of arguments on diagrams involve information external to the diagram. Like you have information usually on the values of phases and their relationships to each other. How do you sort of account for that here? And how sort of complicated can you make that relationship before the tool can't keep up?
And let me just open it. So we can have information on the phases. So here I'm saying for 2 phase gadgets with A and B, I confuse it to get A plus B. And I think what's allowed so far is that so on the left hand side, we only allow one variable per node, and on the right hand side, it could be anything.
If I may hazard a guess as to what the question's about, if during the standard ZX calculus simplification of quantum teleportation, for instance, then in the demonstration, you typically say, suppose the measurement result here is A and the measurement result here is B, and then you simplify some stuff, you have a 2A and a 2B, and then you say, but I know that A is 0 or pi, therefore I can remove this node. And that seems to implement that with the Boolean functionality. And I don't know if it does anything beyond that.
So we need we have 2 options of variable types. We support parametric, which means anything. And the other one is Boolean. So if you have a Boolean angles, it knows that if I have A pi and A pi, if you fuse them, I should just get 0. And it knows that if you specify that the type of A is Boolean. But
I suppose the example of teleportation is the simplest example, but for example, I came back, halfway through the discussion on scalable notation. I'm currently working on a paper that sort of extends the scalable notation. And the tricky thing there is that many of the proofs are proofs of families of rewrite rule, which are proved by induction on types. And this seems quite tricky to do in this kind of a representation or manipulation of diagrams. Because you're not just proving then one rewrite rule, but the whole family of rewrite rule, where there's actually quite a lot of information to sort of track to make sure that the family is correct.
Is that like when you have a wire and you split n labeled wire to like 1 and n minus 1?
Something like that, yeah.
Yeah.
Oh, maybe I can. Oops.
Wait, sorry, wait. Let me.
Maybe I can say about.
Just come here.
Okay, sorry. Maybe I can say a bit about that. I've been thinking about how to do scalable ZX calculus in ZXLive. So currently, it's kind of concrete in the current rules. You are allowed, as of this week, you can do variables that is like these Boolean and symbolic and just fraction like symbolic variables like here. It would be nice to also represent matrices over F2 like in scalable ZX, and more generally other types of matrices like that Robert's working on, like that represent stabilizers, or in QDITS, DISX is not part of physics, it's a separate GitHub repo, just so that we don't break backwards compatibility by changing the underlying graph type data structure, like the dimension of that and the phases, how those are tracked. But it could be just put into you could modify physics to have that. Currently, it's on a separate repo. I do think that implementation wise with scalable ZX calculus, there are quite a few rules that are satisfied by the meta generators regardless of the actual data within the generator. To give a specific example, like these matrix arrows that are like any linear map over F2, these ones they'll commute with Z5 with scalable Z spiders and X spiders in a certain way, and that's regardless of what is the actual linear map over F2. So I'm thinking that probably makes sense to start with these kinds of rewrites that, although it does represent a family of rewrites, it's not difficult in terms of the implementation because it's just a function of what the generators are and is independent of what the actual label is. I also think that there could be quite good rules for control diagrams in ZXW calculus, kind of ongoing work, but then it's also kind of black boxing certain generators so that, well, meta generators such that you don't specify and you don't have to know what is inside the box so long as you can check that it does satisfy one property, in this case that it's a control diagram. So these are things that we're quite interested in, but yeah, there's still quite a few ZXLive features to do first, kind of at this level before doing these meta generators.
So for like physics supports putting arbitrary data on generators. Like, I mean, here we don't have the interface for it, but physics supports any data on any vertex, and it's not that complicated to make the custom rules also aware of the data there. So maybe like a good example here is that like the Z box here. So this Z box, for instance, supports any complex numbers, and the way it's implemented is by using like this arbitrary data on the nodes. So like physics on its own only supports phases that are fractions, and it does not support like arbitrary complex number on nodes. And here we just added the data to the generator. So it's not that complicated to add, like, instead of a complex number, we can have a matrix.
We say it's not that complicated, but actually you will have to do quite a bit of stuff backend wise
Yes,
to do the new generator, and yeah, but At least it's doable. I do think qubits would be a struggle.
Yes, it's doable is the right word. Yeah.
I think it'd be nice to have some rewrites that basically take the basic wire type and can unfold them into multiple wire types. You probably just would add a wire type in the bottom right currently. There's only simple and Hadamard edges, but you'd also have, depending on your preferred, maybe like doubled wires, like thick wires for multiple wires, or even with CPM construction, like double wires or some different kinds of wires if you wanted like quantum data or classical data. That is quite flexible to just add a new edge type.
Yeah, I mean, there's a lot of things we can keep adding more and more, but like, yeah. So it was. I think we need to kind of figure out what people really want, what most people want first. Like for me, I think I really want to add qubits, but I think most people actually work with qubits, so it's maybe more important to iron out those features.
The problem with qubits is that whether it's fleximetric or not will actually really change the implementation. Like the direction of the CNOT really matters now. And then so all the underlying graphs need to be directed if we do it that way. Or you just use fleximetric. But then we have to redefine every generator and rule. So it's not easy.
I have a follow-up to an earlier question. When you have a rewrite rule with both sides and it checks whether or not it has the same semantics, does this technically mean that it does something like n factorial comparisons, trying to make sure that the boundary nodes are lined up? Because unlike quantumatic, the boundary nodes here are not identified.
They actually are. I mean, I think it's giving the wrong impression, but like, oh no, sorry, you're right. No, they're not identified. Sorry, but all it knows that there is a input and then there is an output. So when you match things, it matches, like it uses a graph matching. But when you're like checking the semantics, sorry, I think I misunderstood your question. So when it's checking the semantics, when it's computing the linear map.
Here's a simplified version of my question. If you just take these two nodes and you swap their position, then like I assume that it would still be happy with the rewrite rule.
No.
Oh, okay. So it looks at, like, I guess it solves the Earth mover distance problem, or something similar, and tries to find like the closest like nodes to each. Because what I'm saying is that the nodes on the right are not in the exact same positions as the nodes on the left, so you have to like figure out where they are, and I guess it solves this little problem.
Yeah, so what matters is the order of nodes. So it will say that, okay, there is only one input, and then to figure out a list of outputs, and it can say that, okay, this has to be before this, and so it orders the output number. So there are 3 boundary nodes that it determines to be outputs, and then it orders that this is output 1, output 2, output 3. And it does the same on the right-hand side as well.
So it would be unhappy with a node like this or something that was neither an input nor an output, or I guess it would just declare that it's one of those two.
I think maybe this is a question for John, but I don't know how it would treat like perfectly vertical nodes.
I think it would probably give an error, like an exception. Yeah, so like we're just using the visual information. We're just checking like what is the order from top to bottom, and that's like the order that's like used.
Yeah, that's very clever.
I think a little bit before we also labeled the inputs and outputs, that it was a bit more visually clear which was mapped to which.
Yeah.
I think we should do that again. I think because that's probably quite useful information to have.
We also added, like at some point, like initially, we also added just the ability to label each boundary node that, okay, this is B1, this is B2, this is B3. But that seemed more work than just automatically guessing the inputs and outputs.
I would say that in some cases, not knowing that what the exact algorithm is underneath might make it a little bit difficult to debug whenever you give this like, because if you let me see if I can also draw. I don't know how to draw. but
There's a pencil on the bottom left.
there is a pencil on the bottom left, not on my screen.
If you updated your Zoom within the last like 6 months or so.
I'm not seeing it.
Also view options,
Oh,
annotate.
here, I found it. Yeah, so like you could extend this one more this way and make this one shorter, so that now this is the top one and this is the bottom one, so they would be mapped the other way around. So that would make it a little bit difficult to debug what's going on. But if you have like a just a shortcut thing, it's just you press one button on the keyboard just to see the numbering that the algorithm underneath is assigning, then I'd be happy.
Yeah, I think that's a good point. Yeah, maybe we should just have labels for the input 1, input 2, input 3, output 1, output 2, output 3, something like that. Maybe we should not allow for like editing those boundary labels manually, but let people just reposition, and it will just at least give you feedback of what the node assignment is for boundary.
I agree, and I also want to just mention that for say quantum error correction or other kind of quantum computer architecture where applications, it's quite common that the default is to label the output wires with a qubit number. So that might be behavior that we want to have anyway, because oftentimes it's not so much the order that matters, but if you're writing like a circuit into some like geometry in quantum error correction, then you'd want to label the numbers, because having all the wires sticking out is very ugly.
One feature you showcased is the magic Clifford compilation button. And Clifford compilation is a topic very dear to my heart. So what algorithm did you use for that simplification process?
Let me see if I have this open. I've opened too many things. So it's just the one in physics.
I guess you happen to know what that one uses. I think I've used PyZX for a little. I've mostly used Quantomatic.
Okay, so here these are all the simplification routines that physics supports, and they are just buttons to call those physics functions. So I think I'm honestly not sure what algorithm physics uses for Clifford simplification. Maybe John can comment.
Yes, so what it does is it first converts all the spiders to green by making all the red ones green. Then it fuses all the spiders. Then it does local complementation wherever it can. It does pivots wherever it can. And then it does boundary pivots wherever it can. And it repeats until all the internal spiders are removed. In the case of a Clifford diagram, this always succeeds. And if it's not a Clifford diagram, it just tries to do it as best as possible. And the normal form, the pseudo-normal form you get has a single layer of spiders on the inputs and a single layer of spiders on the outputs that are connected via Hadamard edges, and potentially have Hadamards on the input and output wires. And it's a pseudo-normal form because it's not unique. You get different outputs.
Thank you.
Yeah, we've had a lot of questions already. Maybe I was going to ask Razin, what are the features you want to work on next?
I guess the right now is more important, like iron out certain things and like just have, so like for instance, some of quality of life features that we discussed today, for example, labeling the input output nodes, like all of this is very essential, so we should do that. But like as like a new feature that to add to this, I would like to be able to support custom generators. Partly because I want to do like QDIT stuff, mixed dimensional stuff, like a lot of things that are not qubits, and that's like those are the kind of things that I'm interested in. So supporting that sort of stuff, yeah, I would like to do work on those things. But again, I think before going crazy, I think we should first make the existing functionalities better.
Yeah, I think we should maybe decide on what is like the version 1.0, like what is needed to say, oh, this is 1.0, and we can start adding stuff from there. All right. If there's no more questions from the audience, I suggest we thank our speaker again in however fashion you want to do that in a Zoom meeting. And Razin, thank you very much.
Thank you.
Stop the recording.
Thanks.
Which I do how? Oh, there it is. Okay. Yes, 1, 2.